Okay, in today's lecture, we're going to cover the section 1.8 material, which is an introduction to linear transformations. So let's start by introducing some terminology. So throughout this section and the next section, we're going to be discussing transformations. So a transformation is really just an example of a function, which might also sometimes be called a mapping. Now, in linear algebra, we use primarily the notation or terminology transformation, and we're going to denote a transformation using the capital variable t. So here we would say a transformation t from Rn to Rm is some rule that assigns to each vector x in Rn a vector which is denoted as t of x in Rn. So visually, we can think about a transformation as just a function. So we have some set of vectors x, and for each vector which is in the space Rn, we have a transformation or a function or mapping, which we call t, which assigns a value which we denote as t of x, which is going to be some vector in Rn. So the set Rn, that is the set of values where we're taking the vectors x from, is called the domain of our transformation. And R sub m, or Rm, is what we would call the codomain of that transformation t. It is the space where we are mapping the vectors x into. So the notation that we'll sometimes use throughout this course would be the following. T is mapping from Rn to Rm. So we're moving from n-dimensional space to m-dimensional space. And this notation is indicating that the domain of our transformation is Rn, and our codomain is R sub m. Now, for a vector x in Rn, the vector t of x, which lies in Rm, is called the image of that vector x, or if we need to be a little more specific, we sometimes say the image under the action of t, or under the mapping t. And the set of all images t of x such that x is a vector in Rn is called the range of our transformation. So we might ask ourselves, well, how does the range differ from the codomain? Well, the codomain here, we said, is the entire space Rm. And the range is just going to be some subset of Rm. So here, really, my codomain, which is Rm, all of n-dimensional space, could be visualized as this rectangle. And this set which we have inside of the rectangle, which consists of all of the images t of x, such that x was some vector in R sub n, is called the range. So this subset of the codomain, which consists of all values of t of x, is called the range of our mapping. So the range is a subset of the codomain. The range and codomain are two different sets here. All right. So throughout this course, the transformations which we will be working with most often are transformations or mappings, which can be described using matrix multiplication. So for instance, what we mean by that is if we have a vector x in Rn, the transformation T of x is computed by taking the matrix A times the vector x, where A is some m by n matrix. Now notice here, in order for this to be defined, remember for a matrix product to be defined, A times x, well, the number of columns of A, so that is n columns, has to be the same as the length of the vector x, an n-dimensional space here. So if we have an m by n matrix, then the product of A times x gives us an m-dimensional vector. So we're mapping into Rm. And these types of transformations, which are defined as matrix multiplication, are sometimes denoted more simply as follows. We would say x maps to A times x. So here, again, if A is an m by n matrix and x is an n-dimensional vector, then the domain of T is all of Rn, and its codomain would be all of Rm. Now, that's different from the range. The range of this transformation T may not be all of Rm, but just some subset. All right. So now that we have a little terminology about transformations, domains, codomains, images, ranges, these sorts of things, let's look at some examples where we'll work with these linear transformations. So here in our first example, let's suppose that we have the following matrices. A, which is a 2 by 2 matrix, 2, 0, 0, 2. And then matrices or vectors, u and v, given here. And we're going to define a transformation T from R2 to R2, so that is from the plane back into the plane, by defining T of x as the matrix A times x. So we are asked here to find T of u and T of v. So those are the images of u and v under this transformation T. So let's start by looking at T of u. So remember, this transformation is defined by matrix multiplication. We're supposed to take the matrix A and multiply by the vector u in this case, since we're evaluating T of u. Now here, A was the matrix 2, 0, 0, 2. We're multiplying by the vector u, which was 1, negative 3. So let's see what we get here. So recall for the definition of a matrix times a vector, we would take the first component of our vector as the weight of the first column vector of our matrix. So we have 1 times 2, 0, plus the second component of our vector x, or in this case u, was negative 3, times the second column vector of our matrix, which was 0, 2. So simplifying here, we are left with, for our first component of the vector, 2 minus 0, or 2, and for the second component, 0 minus 6, which leaves us with negative 6. So here, the image of u under this transformation T is the vector 2, negative 6. And if we look at the image of the vector v, well, we take A times this vector v, so that is the matrix 2, 0, 0, 2, times v, which had components as these arbitrary values, a and b. So again, to take this product of a matrix times a vector, we take the first component of our vector A as the weight of the first column vector of the matrix A, plus the second component of our vector B as the weight for the second column of the matrix A. So we're left with 2A plus 0 and 0 plus 2B. So this would be the image of V under the transformation T. So let's think about what exactly this transformation is doing to the given vector. So if we started with the vector u, 1, negative 3, by applying this transformation, we had an image of that vector as 2, negative 6. Notice it's the vector u multiplied by 2. And for a general vector whose components are any arbitrary values a and b, the image of that vector was 2a, 2b. Again, we're just multiplying that vector by the scalar 2. So this transformation T is equivalent to scalar multiplication by 2. Okay. So let's consider another example. In this next one, we have a matrix A, which is some 3 by 3 matrix, and a vector B, which is 3 by 1 column vector. And we're defining a transformation T by T of x is equal to A times x. So again, this transformation is described by matrix multiplication. And we are supposed to find a vector x whose image under the transformation T is equal to B, and determine whether that vector x is unique or whether there's more than one vector which would have an image of B. So we are trying to find the values of the vector x such that T of x, which is defined as A times x, is equal to the given vector B. So here we're trying to solve the matrix equation A times x equals to B, where A and B are known, and we've seen from our earlier sections in Chapter 1 that to solve such a system we can consider the augmented matrix. So here we would say the corresponding augmented matrix would be the following. So we take our matrix A, whose first column was 1, 0, 3, second column was negative 3, 1, negative 5, and our third column was 2, negative 4, negative 9, and we are augmenting that with the vector B. 6, negative 7, negative 9. So if we can row reduce this matrix to row echelon form or reduced row echelon form, then we can find our solution for this vector x. So here in our first row, we already have a leading coefficient of 1, and below that we have a 0, and then the lead entry for our third row is 3. So we need to eliminate that 3 by using the 1 as a pivot. So the first operation I would perform is to take row 3 and subtract 3 times row 1. So our first row remains 1, negative 3, 2, 6. Our second row is 0, 1, negative 4, negative 7, and our third row becomes, we have negative 3 plus 3 is 0, positive 9 minus 5 is 4, and then a negative 6 minus 9 gives us negative 15, and then on the right-hand side, performing the same operation, we would have negative 18 minus 9 is negative 27. All right. So now, in our first row, we have a leading entry of 1 with zeros below it. In our second row, we have a leading entry of 1, and we need to eliminate the negative 3 and positive 4 that appear above and below it. So, to eliminate the negative 3 in the first row, I would take row 1 and add to it 3 times row 2. So my first row becomes 1, 3 minus 3 is 0. We have negative 12 plus 2 would be negative 10. And on the right-hand side, we have negative 21 plus 6, which would leave me with negative 15. My second row, I'm going to leave alone as 0, 1, negative 4, negative 7. And to eliminate the 4 as the leading entry in my third row, I'm going to take row 3 and subtract from it 4 times row 2. So we have 0, negative 4 plus 4 is 0. I have positive 16 minus 15 is 1. And then on the right-hand side, I've got a positive 28 minus 27 is 1. So now, my first two rows both have a leading entry of 1 with zeros above and below. And my third row has a leading entry of 1, but I need to eliminate the negative 10 and negative 4 that appear above that. So in our last step, to put this in reduced row echelon form, I would perform the following operation. So for row 1, I would add 10 times row 3. So that gives me a 1, 0, 0. And then 10 minus 15 is negative 5. And in my second row, I'm going to add 4 times the third row, which makes my second row 0, 1, 0, negative 3. And my last row remains as 0, 0, 1, 1. So now our matrix is in reduced row echelon form, and we can see that the vector x, which would be the solution of the system, has a first component of x1 is equal to negative 5, a second component of x2, which is negative 3, and our third component would be positive 1. So this would be the vector x that satisfies that matrix equation. In other words, the vector x, which if we apply the transformation t to that vector, we get the vector b, which was given in the problem statement. And then the last part of this question asks if the vector x is unique. So that is this the only solution, or are there multiple solutions? And through our row reduction, we found that there were no free variables. There was only one solution. In order to have multiple solutions, we would have to have a free variable. So we can say here the vector x is unique since there are no free variables. All right. So in our next example, we have a matrix A, which is a little bit larger matrix. Here we have a 4 by 4, and we are asked a similar question to what we saw in the previous example. Here, we want to find all of the vectors x in R4, which would be mapped to the 0 vector by the transformation defined by x is being mapped to a times x. So as with that previous example here, we want to look at all of the vectors x such that when I apply my transformation t of x, which is defined by matrix multiplication by the matrix A, I would get an image of the 0 vector. So here I've got a homogeneous linear system defined by this matrix equation, and in order to solve this, I can make use of an augmented matrix as I did with the previous example. So here, the first row of our augmented matrix would be 1, 3, 9, 2. Second row is 1, 0, 3, negative 4. Second row is 0, 1, 2, 3. And our last row is negative 2, 3, 0, 5. And we have a homogeneous linear system, so we are augmenting with the 0 vector as our vector on the right-hand side of this equation. So again, through row reduction, we can find our solution. So for our first row, we have a leading 1, and I need to eliminate the 1 and the negative 2 that appear below that. So for my second row, I could take row 2 minus row 1. So my first row, I'm going to leave as 1, 3, 9, 2, 0. And when I perform this operation, let's see what we have. We've got 1 minus 1 is 0, negative 3, 3 minus 9 would be negative 6, and negative 4 minus 2 is negative 6, with 0 minus 0 giving us a 0 on the right-hand side. My third row, I'm going to leave alone for now. I have 0, 1, 2, 3, 0. And to eliminate the negative 2 in the fourth row, well, there's a few ways I could do it. I could use the leading 1 either from the first row or the second row. Here, just to illustrate maybe a different approach from what you might initially use, I'm going to take row 4 and add to it twice row 2 instead of using row 1. So what would that give us? We would have 2 minus 2 is 0. 0 plus 3 is 3. I would have 6 plus 0 is 6. And negative 8 plus 5 is negative 3, with 0 plus 0 giving me 0. So now I have that leading 1 in my first row with zeros below it. In the second row, I have a leading entry of negative 3. And if I look through my second row, I can see that everything is divisible by 3. So in order to get a 1 for that leading entry, I could divide my second row through by negative 3. So in my next step, one operation I'll perform is to take row 2 and divide by negative 3, or take negative 1/3 of the second row. Now in this same step, I want to try to row reduce a little further. I know that in the first row, I want the second entry to be a 0. So an easy way to get a 0 in that first row would be to add row 2 to row 1. So I'm also going to take row 1 and add row 2 to this. So first, by dividing my second row through by negative 3, our second row becomes 0, 1, 2, 2, 0. And when I add my second row to the first, my first row becomes 1, 0, 3, negative 4, 0. All right, now I'm going to leave my third row alone for now. I've got 0, 1, 2, 3, 0. And in this same step, the positive 3 that I had for the leading entry in my fourth row, I can eliminate if I were to add the second row to it. So I'm also going to take row 4 and add row 2 to that value, which makes my fourth row 0, 0, 0, negative 9, and 0. All right. So now I have a 1 as the leading entry of my first row with zeros below it. I have a 1 as the leading entry of my second row with zeros above it, I just need to eliminate the 1 below it. So in this step, I'm going to take row 3 and subtract row 2, which leaves me with a first row of 1, 0, 3, negative 4, 0. Second row of 0, 1, 2, 2, 0. And my third row becomes 0, 0, 0, 1, 0. And in this same step, I know for my fourth row, I want the leading entry to be a positive 1. An easy way to get a positive 1 there would be to divide my last row or fourth row through by negative 9, or equivalently multiply by negative 1/9, which makes my fourth row 0, 0, 0, 1, 0. All right. So now I have, for my first and second rows, leading entries of 1. For my third row, I have a leading entry of 1, which I need to eliminate the constant 1, 2, and negative 4 that appear above and below it. So in my last step, I'm going to take row 1 and add 4 times row 3, which makes my first row 1, 0, 3, 0, 0. I'm also going to take row 2 and subtract from it 2 times row 3, which would give me 0, 1, 2, 0, 0. My third row is 0, 0, 0, 1, 0. And I see that my third and fourth rows are identical, so to eliminate 1, I could take row 4 minus row 3, which would give me a row of all zeros. So our matrix is now in reduced row echelon form. And we see that we have pivot columns in the first, second, and fourth column. And I do not have any pivot in the third column. So here we would have a free variable for our third variable, or our third column, x3. So let's say here, let x3 be a free variable. And using our reduced row echelon form matrix, we find that x1 would be negative 3x3 from our first row. From the second row, we have x2 would be negative 2 times x3. Of course, x3 is a free variable. And then using the third row in this matrix, we have 1 times x4 is equal to 0. So x4 is 0. So expressing this answer in vector form, we would have the vector x, which is found by taking the free variable x3. And for our first coefficient of the matrix, we had negative 3 times x3. For the second coefficient, or second entry in this vector, we had negative 2 times x3. X3 itself can be thought of as 1 times x3, and x4 was 0. So whatever value we choose for the free variable x3, if we factor it out from each component from this vector, we have negative 3, negative 2, 1, and 0. So here we have infinitely many vectors of this form that would be mapped onto the 0 vector by this transformation. Okay. So in our next examples, we're going to start considering how certain matrix transformations can be interpreted geometrically. This is particularly easy if we're considering vectors in R2, or vectors in the plane. So let's suppose that we have a transformation T, which is defined as T of x is equal to the matrix -1, 0, 0, -1, times a two-dimensional vector whose components are x1, x2. So in this example, we are asked to plot the vectors u, which are 5, 2, and v, which is -2, 4, as well as their images under this transformation of T, and then describe geometrically what this transformation T is doing to each vector in the plane. So let's start by sketching the vectors themselves. Here, u was the vector 5, 2. So its position vector representation would have its initial point at the origin and its terminal point as 5, 2. So moving to the right 5 units and 2 units upward, we have the following representation of the vector u. Now our vector v was -2, +4. So from the origin, to get its position vector representation, we would move 2 units to the left and 4 units upward. So this would be a sketch of the representation of the vector v. So here let's consider the transformation of each of these vectors, or the image of each of these vectors under that transformation T. So here we would look at T of u, which is defined as the matrix -1, 0, 0, -1, times the vector u, whose components were 5, 2. So we have the first entry of the vector u was 5 times the vector -1, 0, plus the second entry of u, which was 2 times 0, -1, which leaves us with a first component of -5 and a second component of -2. So in this right-hand figure, let's see what exactly this transformation is doing. So for the transformation of u, we have the vector -5, -2. So we're moving 5 units to the left of the origin, 2 units downward. So we would have the transformation of this vector u shown here. So how does that seem to compare to our original vector u in the left-hand plot? Well, it appears to be moving in the exact opposite direction. It has the same length, but instead of moving to 5, 2, it's moving to -5, -2. We've just reversed the direction of that vector. So let's see if the same thing happens with the vector v. So for T of v, we're taking the matrix -1, 0, 0, -1, and multiplying by the vector v, which was -2, 4. So we have -2 times -1, 0, plus 4 times 0, -1. So here we have a +2 and a -4 as the components of our image. So for the representation of this vector, we start at the origin. We are moving 2 units to the right and 4 units downward as the image of v. So comparing that with the original vector v, we see again that it appears to have reversed the direction of that vector. So geometrically, to describe what this transformation is doing, we could say geometrically the transformation t reverses the direction of a given vector. Another way which we could think about this is as reflection of our vector through the origin itself. Our initial vector u was shown here in red. Its transformation was the following vector. That is the vector that was achieved by reflecting the given vector u through the origin. And the vector v had an image shown here. So we could see that the original vector v was reflected through the origin to get its image. So here we could think about this as reversing the direction of a given vector, or reflection through the origin. All right. So let's look at some other examples with geometric interpretations. So for our next example, we have a transformation t, which is defined by t of x is equal to the matrix 0, 1, 1, 0 times the vector x, whose components are x1, x2. So similar problem here. Again, we want to plot the vectors u, which was 5, 2, and v, which is negative 2, 4, and their images. So here, let's look at the vector 5, 2. Same vector that we had in the previous example. So drawing its representation, we have this vector u, and our vector v, negative 2, 4. Let me maybe plot on the left-hand plot here. We have negative 2, 4 for this vector v. So let's find the image of each vector under this transformation and then describe what this transformation is doing geometrically. So for the image of u, we're looking for t of u, which is found by taking the matrix 0, 1, 1, 0, and multiplying by u, which was the vector 5, 2. So this gives us a 5 times the vector 0, 1, plus 2 times the vector 1, 0. So that leaves us with 2, 5 as the image. So here the vector 5, 2 has mapped to 2, 5. So let's sketch the image of that transformation, or of this vector u. So now we are moving 2 units to the right and 5 units upward. So this vector would be the transformation of that vector u. And let's see what happens with v. So t of v is the matrix 0, 1, 1, 0 times v, which was negative 2, 4. So this gives us a negative 2 times 0, 1 plus 4 times 1, 0, which leaves us with an image of 4, negative 2. So as with u, where the image reversed the components of our vector, for the vector v, negative 2, 4, the image was 4, negative 2. So let's sketch its image. So now we are moving 1, 2, 3, 4 units to the right and 2 units downward. So this would be the image of the vector v under that transformation. So what appears to be happening here, well, if we compare our original vector to its image, it looks like we are reflecting the given vector about the line y equals x, or if we're considering points in the x1, x2 plane, we're reflecting about the line x1 equals x2. That is the line through the origin of slope 1. So here the line x1 equals to x2 is shown here in black, and we can see from our sketches that we are reflecting the given vector about that line. So for this one, geometrically, we have reflection about the line x1 is equal to x2. Okay, so let's look at some other ones. In the next few examples we'll consider the geometric interpretation for, we'll see examples of what is called a linear transformation. So let's define what it means for a transformation to be linear. So there's a two-part definition here. A transformation T is called a linear transformation if the following two properties hold. First, if the transformation of the sum of two vectors, u plus v, is equal to the sum of the transformation of u and v for all u and v in the domain of that transformation T. And secondly, the transformation of a constant multiple of the vector u is equal to the same constant c times the transformation of u for all scalars c and for all u in the domain of T. So in summary, linear transformation will preserve the operations of vector addition. That is, the transformation of a sum is the sum of the transformations of the vectors. And scalar multiplication. The transformation of a scalar multiple of a vector is that same scalar times the transformation of the vector itself. And it can be shown that every matrix transformation is indeed a linear transformation because of the properties of matrix multiplication that we saw in our earlier sections of Chapter 1. Now, we have a couple of properties that linear transformations satisfy that are relatively nice properties, or these will give us ways to test whether a transformation is linear. So some basic properties of linear transformations are the following. If T is a linear transformation, so if it satisfies these two conditions, then the transformation of the zero vector must be equal to the zero vector, and the transformation of some linear combination of two vectors, say a constant c times u plus another constant d times v, is equal to the linear combination of those transformations, c times t of u plus d times t of v. So that second property really follows immediately from properties 1 and 2 of the definition, as well as this first property where t of 0 is equal to 0. All right. Now, in general, this second property of a linear transformation, where the transform of a linear combination is the linear combination of the transforms, holds for more than a linear combination of just two vectors. So what I mean by that is if we're taking the transform of a linear combination of p vectors, that is the same as the linear combination of the transforms of each of those vectors. And this property is sometimes referred to as the superposition principle. All right. So in our next example, we'll consider a certain type of transformation, which can be described as a contraction or a dilation of a vector. And we're going to see that such a transformation is linear. So in this next one, let's suppose that we are given some scalar. So that is just a number r. And we define a transformation t from the plane to itself as t of x is equal to the scalar r times x. So here our transformation, we're just taking a scalar multiple of some vector x. So this sort of transformation is called a contraction if the scalar r is between 0 and 1. That is, if we're shortening or contracting the length of our vector, multiplying by a scalar between 0 and 1. And it is called a dilation if the scalar r is greater than 1. So say if we were taking 2 times a vector, we would be looking at a dilation. If we were taking 1/2 of a vector, that would be a contraction. So here we are supposed to show that either a contraction or a dilation is a linear transformation. So recall there's 2 properties that we have to show for a transformation to be linear. The first thing that we need to check is whether the transformation of a sum of 2 vectors, let's say u plus v, is equal to the sum of the transformations. Now, based off the definition of this transformation, t of x was defined as r times x. So here, for t of u plus v, we're taking r times the sum of u and v. Now, properties of a scalar multiplication and vector addition say that this is equivalent to taking r times u plus r times v, but this is exactly the transformation of the vector u plus the transformation of the vector v, since our transformation was to just take the vector u or v and multiply by the constant r. So it satisfies the first condition for linearity. The second condition that we have to check is that the transformation of a scalar multiple of a vector u, let's say c times u, is equal to c times t of u. Now here, we're defining our transformation as the constant r times our vector, which was c times u. So distributing our r, or just using the definition of scalar multiplication, we can think of this as r times c times the vector u, and we know that for scalars, r times c is the same as c times r. So we have here a scalar c times the product of r with u, but the product of r times u is exactly the transformation of u. So here, this sort of transformation, either a contraction or a dilation, is a linear transformation. It satisfied both conditions of the definition. So here we have established that t is a linear transformation. Okay. Now, in our next example, we'll consider how we can define a linear transformation, or by looking at the transform of two specific vectors. So let's consider the following vectors. Let's say that we have E1, which is a vector 1, 0, and E2, which is a vector 0, 1. And we have a transformation T from the plane to itself, which we are told is a linear transformation that will map the vector E1 to Y1, which was 2, 1, and it maps the vector E2, which was 0, 1, to Y2, which was negative 1, 3. So from here, we are asked to then find the images of each of the following vectors. So for part A, we have the vector 5, negative 3. So if we don't know what the transformation is defined as, we can't just apply the transformation directly to this vector A, but we do know two vectors, E1 and E2, and the images of those two vectors under this transformation. Now, what's special about these vectors E1 and E2 is that they are called standard basis vectors for R2, which we'll discuss a little bit later in more detail in our course. But these vectors are special in that we can write any vector as a linear combination of those two. So in particular, the vector that I'm given here, 5, negative 3, can be written as 5 times 1, 0 to get the 5 for that first component, and then plus negative 3 times 0, 1 to get negative 3 in that second component. So this is exactly 5 times the vector E1 minus 3 times the vector E2. So if I want the image of the vector A under the transform T, that is T of A, well, that's the same as looking at T of 5E1 minus 3E2. But since T, we were told, is a linear transformation in the problem, well, the transform of this linear combination of the vectors is the same as the linear combination of the transform of these vectors. That is 5 times T of E1 minus 3 times T of E2. But we know the images of these vectors E1 and E2. They were Y1 and Y2. So here we'll have 5 times the transform of E1 was the vector Y1, which was 2, 1, minus 3 times the image of E2 was the vector Y2, which was negative 1, 3. So now performing a little vector algebra, we have for our first component, 10 plus 3 is 13. And for our second component, 5 minus 9, or negative 4. All right. So we have found the image of that vector A under the transform T just by looking at the image of these vectors E1 and E2 under that transform. So again, this is illustrating something we're going to consider a bit more in the next section and later in the course, where these two vectors, E1 and E2, are called the standard basis vectors for the plane, and these allow us to rewrite any vector as a linear combination of those two vectors. Now let's say that we wanted to define our transformation T for any vector in the plane, not just a vector that we saw in part A. So if we want to generalize this, let's consider the vector B, whose components are arbitrary. Let's say any point x1, x2 in the plane. So as we did in part A, I could write this vector in terms of E1 and E2 as x1 times 1, 0 plus x2 times 0, 1 which is the same as x1 times e1 plus x2 times e2. So taking the image of this vector b under the transform t, well, b is the same as x1 e1 plus x2 e2. And since we were told t is a linear transformation, this is the same as x1 times t of e1 plus x2 times t of e2. Now, we know the images of e1 and e2 under this transform, so we have x1 times y1, which was 2, 1, plus x2 times the image of e2, which was negative 1, 3. So we're left with, for the image, 2x1 minus x2, and x1 plus 3 times x2. So this is the image of any vector whose components are x1, x2 under that transform. So we now have a formula to get the image of any given vector under the indicated transform. And one thing to notice that we're going to look at in some more detail in our next section, if we look at the image of this transform, if we look at the coefficients of x1 in each row, the coefficients were 2 and 1. So notice that those were the entries of this first vector y1. And if we look at the coefficients for x2 in each row, negative 1 and positive 3, well, those were exactly the entries of this vector y2. So it seems like there is some relationship between our transformation and the images of these two special vectors, e1 and e2. We'll see that in more detail in the next section. So let's look at a few other transformations to finish up this section, which have geometric interpretations, and we'll see that these are also linear transformations. So here we are considering a transformation T, which is defined by T of x is equal to the matrix 1, 3, 0, 1 times our vector x, whose components are x1 and x2. So this is a transformation from the plane back into the plane. So as with our earlier example, we are told here to plot the vectors a, which are 2, 0, and b, which is 0, 2, and c, which is defined as the sum of a and b, which would be the vector 2, 2. And then we also want to plot the images under the transformation T. So let's start by plotting these vectors themselves. We have here the first vector, A, which was 2, 0. So from the origin, moving 2 units to the right, 0 units upward or downward. We have a vector B, which was 0, 2. So moving from the origin to the point 0, 2. And then we had the sum of these two vectors, C, which was 2, 2. So we're moving from the origin to the point 2, 2. We can see that sum represented here by the parallelogram rule. So if we think about a parallelogram formed by the vectors A and B, we see that we have a little square here, and the diagonal of that square is the vector C, their sum. All right. So let's look at the image of each of these vectors under the transformation T. So looking at T of A, Well, this transformation is defined by taking the matrix 1, 3, 0, 1 and multiplying our vector. And here our vector was A, which was 2, 0. So we have 2 times the first column, 1, 0, plus 0 times the second column, 3, 1. So this leaves us with 2, 0. So the image of the vector A, which I had shown in red, is 2, 0. So it is its own image under this transformation. We have T of A. So let's look at the transformation of B. T of B is the matrix 1, 3, 0, 1 times the vector B, whose components were 0, 2. So here we have 0 times the first column, 1, 0, plus 2 times the second column, 3, 1. So that leaves us with 6, 2 as the image of B. So the vector B is transformed under T to the vector 6, 2. So we're moving 1, 2, 3, 4, 5, 6 units outward, 2 units upward. So we have the image of B under the transform T shown here. And then the transform of C, which was the sum of A and B. Well, since T is a matrix transform, it's defined as a matrix times a vector, we know that it is a linear transform. We said earlier all matrix transforms are linear. So this would be equivalent to T of A plus T of B, which we found in our earlier work. So we would have T of A, which was 2, 0, plus 6, 2, which gives us 8, 2. So the transform of our vector C would be the vector 8, 2, shown here. And again, since this transformation is linear, well, each of the vectors, A, B, and C, are transformed to the following vectors, and we see that T of C is, again, the sum of T of A and T of B, which were shown here in red and blue. So the sum was illustrated using the parallelogram law. So this original little square that we had, which was a 2 by 2 square in the plane, is mapped to this parallelogram shown here. So we've sort of taken our square and stretched it horizontally in this direction. So this sort of transformation is referred to as a shear transformation, where we have the image of some square in the plane is some parallelogram. We said that we have sheared this square in a horizontal direction. Okay. So in our next one, let's consider a similar problem. Suppose that we have a transformation T defined by T of X is the matrix 0, negative 1, 1, 0, times the vector x1, x2. And here we are asked to plot the vectors A, which are 4, 1, B, which is 2, 3, and C, which is the sum of A and B, which is 6, 4, as well as their images under the transformation T, and then describe this transformation geometrically. So starting with our first vector 4, 1, we have our representation shown here for the vector A. B is the vector 2, 3. So the vector shown here. And then C is defined as the sum of A and B, which is 6, 4. So using the parallelogram rule, we have the following vector for the sum. So again, we can see this by constructing the parallelogram, which has these adjacent edges, and taking the sum as the vector from the origin across the length of that parallelogram. So let's look at the image of each of these vectors under our transformation. So starting with T of A, we're taking the matrix 0, -1, 1, 0, and multiplying by the vector A, which was 4, 1. So here we would have, for our product, a 4 times the first vector, 0, 1, plus a 1 times the second column vector, -1, 0. So this leaves us with a -1 and +4. So the image of the vector A would be -1, +4. So this is our image of A. Now for the vector B, we have T of B would be defined as the matrix 0, -1, 1, 0, times the vector B, which was 2, 3. So we have 2 times 0, 1, plus 3 times -1, 0. So we're left with -3, 2. So here the vector -3, +2 is shown here. So notice that for our vectors A and B, we reversed the components and made the first component negative. And so let's look at the transformation of C. So here T of C is the same as T of A plus B, since C was the sum. And since this is a linear transformation, since it's defined as a matrix transformation, we know that this is the same as T of A plus T of B. But we've already found these values. T of A was -1, 4, plus T of B was -3, 2. So we have the vector -4, 6. Again, if we look at the original components of the vector C, 6 and 4, well, we've reversed them and made the first component a negative. So here, -4 to 6, we have the vector shown here. So again, we see that this sum can be thought of using the parallelogram law. And if we think about the relation of this original parallelogram formed by these vectors And the parallelogram we've obtained from looking at the transforms, well, it looks like it has been rotated. So if we were to rotate this original parallelogram counterclockwise, we appear to have the parallelogram shown as our output here. So this is an example of what is called a rotation or rotational transformation. And here we have a rotation. It's not as obvious from the picture. This is describing a rotation counterclockwise. By an angle, I'm going to call it theta, of pi over 2 radians. All right. Now, in most of the examples that we've been considering, where our transformation is defined by matrix multiplication, we've seen that the transformation has to be linear based off properties of matrix multiplication, but not every transformation is linear. So in our last example, in the following example, we will denote a column vector written as a row. So for notational simplicity here, the vector x will be written as x1, x2, instead of x is x1, x2. And the image of x under the transform t of x, will be written as t of x1 times, or t of x1, x2. All right. So we're going to consider the following transformation. So here we are asked to show this transformation t from the plane to itself, which is defined in the following way. T of a vector x1, x2 gives us a two-dimensional vector whose first component is defined as 4x1 minus 2x2, and the second component is defined as 3 times the absolute value of x2. We need to show that this transformation is not linear. So we need to show that there is some property which does not hold for linear transformations. Now, one property that we want to check is linearity. Is the transform of a linear combination of vectors equal to the linear transformation of the linear combination of the transformation of those vectors? So as sort of a guide here, we can see that it looks like it's probably the second component of this transformation, the part involving the absolute value, that will make this not linear, because the first component is a linear equation of x1 and x2. So let's see if we can exploit that absolute value condition to show that this is not linear. So one way to consider this is as follows. Let's look at the images of the vectors. Let me call them x, which is given by, let's say, 0, 1, and y, which is 0, negative 1, under the transformation t. So looking at t of x, which was the vector 0, 1, well, the first component is defined as 4 times x1, so that is 4 times 0, minus 2 times x2, which was 1, so we're left with negative 2. And the second component is 3 times the absolute value of x2. Now the absolute value of 1 is 1, so we have negative 2, 3. And t of y, which was 0, -1. So if I just make the x2 component negative, I have 4 times x1 would be 0, minus 2 times -1 is positive 2. And for the second component, I have 3 times the absolute value of x2. The absolute value of -1 would be positive 1. So I have a positive 3 there. Now let's consider the sum of these values. So if I were to look at t of the sum of x and y, I should, if this is linear, have t of x plus t of y. Now let's see if that's true. Here, x plus y gives us the vector 0, 0. Now, if we evaluate our transform at 0, 0, we would have 0 and 0. If x1 and x2 are both 0, by substituting into the formula for our transform, we get back the 0 vector, 0, 0. However, looking at t of x plus t of y, well, t of x was this first vector that we found, -2, 3. And then adding the second vector, t of y, which was 2, 3. We get back the vector 0, 6, which is not the same as what we had for the transform of x plus y. So since this linearity condition did not hold, the transform t is not linear.